Yeah, just a little bit about myself. Yeah, I spent many years in semiconductor industry. A company called Maxim Integrated that got acquired by Analog Devices, and I also taught undergrad electronics 1 and 2 and a grad level mixed signal design course at University of Massachusetts, and then. I said I had enough of semiconductor industry. Forget it. I went into more of a, like a system design, like tiny little systems, wearable systems. So last 10 years I spent at Bose, not doing semiconductor design, but doing more of a system design. And actually, I spun up a course at Tufts University called Variable System Design, and I ran it for a couple of semesters as well. And I had this introductory slide for my students back in the day. I always said, hey, listen, this is for undergrad, so pardon, the simplicity. It says, yeah, you start learning about basic stuff like calculus, physics, and chemistry, and then you kind of work your way up. And I said, it's like building a tree, right? You need the strong roots to understand basic math, physics, chemistry, but then it's the trunk that kind of holds everything together. And I called the trunk that the strongest part of the tree is, you need to learn circuits, signals, and electronics. And then actually, this may have been to my grad students, and I said that at the end, grad students who decide to go in the integrated circuit design, right? You're kind of picking one of those branches on the tree, but the trunk has to be strong. So that's kind of where we are today. Word design has been thrown around in many different contexts. So when we're talking about integrated circuit design happens at many different stages. I could be designing a system architecture. Usually in the industry, these guys are called application engineers. They go visit customers, they visit other companies. I'll just use, let's say, Bose. Analog Devices comes to Bose, says, hey, please tell me what you need in the next couple of years, or what you're working on, what kind of improvement do you need? So those guys sit and they kind of figure out topology, circuit architectures, definition of a new chip that they would end up designing. And those kind of specifications kind of flow down and said, okay, once they settle on some kind of architecture, they pass it off to circuit designers. That's the main topic maybe of today. So there'll be an army of circuit designers that take these specifications and literally draw out circuits either on a transistor level or gate level for digital stuff, and run them, simulate them, so on and so forth. Then the design moves towards what's called physical design. So very kind of similar to what you would do in a PCB design, right? You have some idea, you do a circuit design, and somebody lays out the board. So somebody has to lay out the whole chip. And then, the whole thing moves into manufacturing. The guys who work there, it's a special breed of electrical engineers who are, half physicists, half chemists, half electrical engineers or something. Who understand materials very well, who understand device physics, who understand the whole manufacturing process. And then, there's a whole, group working on simulations and tools, the electronic design, automation tools, and so on. And it I don't know, maybe where most of us, well, yeah, all of us maybe operate this on this right side, right? We get these finished products in different packages, we populate our boards, and then we add a whole ton of other stuff to the system. So when we talk about integrated circuit design, it's kind of what you might call it, like three categories, and actually they have a totally different approach when you're designing these type of circuits. So classic analog, like amplifiers, right? Usually you'll find classic analog stuff on the RF side, right? You're receiving and sending very tiny signals, all sorts of front ends, all the fun stuff, the mixers, the multipliers and modulators in RF systems. Logarithmic apps want to sample and hold and track and hold circuits and oscillators. Those type of circuits will have a different design flow than maybe the ones that we are thinking of usually when we talk about IC design, which is this digital, or they use this acronym VLSI, very large scale integrated circuit. So your microcontrollers, graphic processing units, neural network processing units, or neural processors, and so on, or DSPs and whatever not. And then there's this world in between where you kind of mix the analog and the digital, hence the name mixed signal, and maybe the classic ones is ADCs, right? It takes an analog signal, does something to it, converts it to digital, right, and so on. Also in the semiconductor world, right, they talk about these three terminologies or types of products. You know, a standard product, it's kind of the vanilla stuff, right? It's an op-amp. Oh, you know, I know back in the day used to be this op-amp 741 that they use it in classes to show architectures of amplifiers, and kind of everybody learned the IC design from that old design, which is like, I don't know now, 50 years old or something. There's something called application-specific standard products. An example would be kind of the stuff we use in our boards. You pick up STM, you pick up Nordic chip, or whatever you're designing. So those are specific for something that you're doing, but they're standard, meaning it's available to everybody. I can buy it, you can buy it. And there's a whole category of application-specific ASIC chips. An example would be an Apple's H3 processor. Can I buy it? No. Right? It's special made for them. They designed it, somebody makes it for them. So it's very specific for them, and they, you know, nobody else gets to buy it or take it or whatever, license it. So, well, how do I even start? Like, where does the design start, right? I think I'm hoping, you know, these types of figures don't bring up bad memories, you know, looking at transistors and circuits and so on. You know, it's a long story, but you know, back in the day, I hated electrical engineering. Everything about electrical engineering, you know, I just didn't understand in high school anything, like, you know, Ohm's law. But once I kind of, I had some professors who kind of broke the barrier for me, and now that I think in retrospect, I don't think I could have done anything else in my life but do electrical engineering. So, but anyways, yes. So this may bring up some, you know, like, you know, that class I barely passed. I mean, this is the workhorse of today's electronic industry, right? And kind of in subsequent slides, I will be talking about feature size. Oh, so many nanometers. So let me just quickly explain what that means. So why MOSFET? Why this type of a transistor? Right? There are other types of transistors, like a bipolar transistor. Why is nobody using that or not using as much? It's because, right, they can scale it. It's a scaling game. I can make it smaller and smaller and smaller and pack in more transistors, you know, every year, like Moore's law, right? Gordon Moore said, you know, every whatever, how many years, the density of transistors in a chip will double or something like that. So, and you know, why? Well, first of all, it's the technology that allows you to scale, to kind of crunch everything down. And it's also, you know, maybe the first thing I should say, it's an economic thing, right? That people have figured out how to make money, right? If you couldn't make money out of this and scaling and putting more and more of these, right, people wouldn't be doing this. I don't know, it's kind of interesting, right? You have this component, right, that has a couple of terminals, like let's say 3 or 4 terminals. And like this is a photograph, right, of the transistor. You know, it doesn't even look anything like that because it's like picture from the top. And yet when I combine, you know, pick a number, 1 trillion of these, they run your code, right? You write some code, if statements, for loops, you know, processing signals, doing this and this, and that little thing does it, right? Or I should say maybe combination of those things do that kind of fancy stuff. So when we talk about IC design, maybe this slide is a little bit more geared towards, oh yeah, I'm sorry. So what they care about is the size of the gate. So what's the smallest, the shortest and the most narrow part of the transistor, the stop part, the split. What is the smallest dimension they can produce, right, on the wafer? So that's kind of determines when they talk about feature size. So where we are today is when you're talking about digital chips, purely digital, a CPU, right? You are talking about feature sizes, so sizes of the transistors, these black boxes and these other boxes that are an order of 45 nanometers and smaller. The latest technology, right, that TSMC, the Taiwanese company that's kind of pushing the boundary on the transistors, they're pushing towards 3 nanometer, and they only have one customer, Apple. At these types of these dimensions, you're talking about layers in the transistor. You can see it's like a sandwich, right? That are few atoms thick, few atoms of silicon thick. Now imagine making trillion of those reliably and in millions of processors, right? So what could go wrong? A lot of things could go wrong. Like one broken transistor could break a trillion transistor circuit. There are techniques to handle that, but anyways. So in the analog space, the analog guys who do kind of RF and whatever not, they hate small transistors. They're terrible in terms of analog performance, noise, power, bandwidth, and whatever. They like to stay in these higher, older technologies. And kind of today, the analog design are getting pushed down to 22 nanometer size transistors. And they're like, oh, it's too hard. If you need something smaller, if you have a lot of digital circuits, they'll make one circuit in digital technology, like let's say 3 nanometer. They'll make the analog part in something easier. And then they'll put two dies together, bond them, and package them in a piece of plastic. I forgot to send this along the way. So these are some examples of chips. I'll send them around with the little binocular. One of them is open, so you can take and kind of zoom in, and you can see one of these kind of chips that's packaged. The plastic is melted, and the other one has a little, the big one has a little metal flap. You can open it. Yeah, this one you can open the flap and you can actually see it inside. Don't touch it with your fingers. So in this space, right, so you're talking about resistors who have terrible accuracy, capacitors are really small, inductors that are almost non-existent. Yes, you can use some BJTs, right, but they're very few and they're bulky, terrible, but they give you, faster speeds and lower noise. So, and you have to change your way of thinking. Because you have these abnormal inaccuracies in components, you have to think about ratiometric designs. So it's a different breed of design thinking. Kind of up till, I don't know, a few years ago, not few years, maybe 10 years ago, the main workhorse was the MOSFET, as your classic transistor, right? And as the thing shrunk down, this MOSFET started falling apart. It's not working as it's supposed to work. It's like, that controlling gate is not able to hold the control over the channel underneath. So people said, let's build more of a three-dimensional transistor. So this idea of what they call FinFET, like a shark has a fin. So they figure out this new FinFET topology where the channel that's conducting current kind of sticks out vertically, and I take the gate and I kind of almost like wrap it around. So it's almost like you're choking somebody. And then as things move smaller and smaller and smaller, this gate, even though it's circling around the channel, it's like still not good enough. We need to move to something called gate all around. So you're literally, like if you take somebody, choke their necks, like, on and off, right? I need to be able to turn the transistor on and off. The problem is when you're trying to turn it on, you don't have as strong of a choke, and you're trying to turn it off. When you release, there's still some leftover feeling, right? So that's why these different gate topologies allow you a bit more control over the transistor. I'm going to skip this one because I'm running out of time. So when you're talking about the design of integrated circuit design, it's a struggle, right? So it has to be very well thought out. So you kind of start top down. There's many levels of abstraction. So when I am designing a microprocessor, I'm not thinking about MOSFET individual. maybe I'm not even thinking about logic gates and or whatever. I'm starting to think higher and higher levels of abstraction. I'm thinking about memory modules, I'm thinking about arithmetic units or whatever, right? So depending on the complexity, there are different levels of modeling and design that you do. I have to start skipping slides. In terms of analog design, all the fun words, you know, gain, linearity, noise, speed, you know, swing, voltage swing, output, input, impedance, like, oh my God, you know, how do I do it? And the guys who do analog design, right, deal with circuits like this. So they deal with circuits on a very basic level, you know, individual transistors, you know, different feedback topologies. You got to bias it right, you got to size it right, and so on. So the guys who do analog design are actually different from guys who do digital design. So they are a little bit more, let's call it scientific, right? So they have a very defined flow. I say, okay, what do I need to design? I have these abstraction levels, like, and I use Verilog VHDL, and I can write function of my chip in code, compile it down into logic gates. So that's called synthesis, right? So you can synthesize your circuit. Then once you get the synthesized into gates and or inverters, whatever, buffers, then you move that data and you start placing in a chip. And then that's when the fun starts, right? That it's easy, everything is great in code, right? You don't have to worry about speed, you don't have to worry about propagation delays, you have to worry about any of those aspects. But once you get down to the physical world, you start laying out the chip, you have to start worrying about propagation delays, skew, jitter, all the fun stuff. You have to kind of do the timing and whatever else not.
So as we do not have any questions right now, you can feel
okay. All right, I'll try to wrap it up really quickly.
No, you don't have to. You
okay.
can use a bit more time.
So the guys who, you know, there's another, let me call it category of engineers that work in the semiconductor world that are, their main focus is simulation and verification. And this is especially prevalent in a digital design, right? So imagine you're designing a RISC-V based design. Well, how do you know that when you tape it out, when you produce the chip, it's doing what it's supposed to do, right? With all the inputs and outputs and, you know, data moving from the memory and doing all the work in the instruction set and whatever not, right? Somebody has to sit and simulate everything. So that is kind of a whole new world of how do you verify performance of the chip before you actually go and make it, right? Layout, the physical design is again on another level. Those guys, you know, we who do like a lot of PCB design, you know, we take care of certain things, but this, you know, on a chip level, it's a whole different ball game in terms of a layout. It's just far more complicated. Yeah, at the end of the day, you get kind of a microchip that says, you know, this is just from the screenshot. It says, looks great, all these different subsystems, routing, chip, you know, memory or whatever, processors, and it looks great. All right, so also remember the design. I said design isn't just me putting transistors, simulating, and so on, right? Somebody has to package the chip once it's produced, right? So today, you know, you've experienced all sorts of different packages. Packaging is a big game. It's a big task, right? As, like I said, you know, if your analog and the digital can't sit on the same chip, right? I have to sit on a different chip. Well, how do I combine it, put it on a substrate, encapsulate it? How do I want smaller chips. So can I, you know, people want to stack chips three-dimensionally. So this whole packaging game, the thermal consideration is a whole another ball game, like a different breed of electrical engineers. Testing, design for test and manufacturing test, right? You wouldn't want to buy your iPhone if somebody, you know, if there was a chance that it wouldn't work, right? So, well, guess what? Somebody has to test the crap out of it before they sell it to you, right? And the testing happens, you know, from every chip in that system, every component up to the board level, and then on the system level, right? Imagine how much testing goes in let's say, a cell phone. So this is, so how, you know, in the design process, right? What does it take to make a chip? You know, you're talking about a team of 20 to 200 engineers. You know, depends on size of the chip, right? every engineer in the semiconductor world makes quite a bit of more money than we, the lowly guys in the embedded world. So kind of figure of merit is 350, maybe 400K per year. Is a guy who works in a semiconductor, like a mid-level, maybe senior level IC designer, both analog and digital and RF, right? When you're talking product definition, what I make, I want to make sure I can sell. So it takes a time to talk to customers and say, what do you want, what do you want, what do you want, kind of put it all together and make a chip that everybody will buy, right? So product definition takes quite a bit of time. Now, when you decide that you know what you want to make, well, it takes a year at least, and more, 3 years to design the chip, simulate it, verify it, so on, right? You need software, that costs $5 to $20 million per year to license. The whole verification, remember, you're making a new neural network processor, it has 8 RISC-V cores, blah, blah, blah. Well, somebody's got to simulate that and make sure it's actually working before I actually go and make it. So you might end up spending months or even a year in just verification simulation. When it gets to the fabrication, state-of-the-art fab costs anywhere between $20 and $100 billion. Okay? I skipped this part because there's no time, right? How does the fabrication happen? So forget about that. But it happens through masks, right? I got different masks, I shine light, different materials, interactions happen, and I kind of build the chip as a sandwich, right? Well, I need those masks, what they call reticles. Each one of those reticles, it could be about 100 to 150 reticles through which I shine the light to draw the features on the chip. That set of reticles costs anywhere between $100K and $10 million. You make one mistake in your connection somewhere, you wasted $10 million. Hence, importance of verification. Once I start making chips, again, depending on the process, whatever, right, they can cost anywhere between $1,000 to $100,000. So that's a wafer, right? So you get a wafer. I should have brought one that has little boxes of chips, and then you cut them and package them and sell them, right? Well, guess what? Then you have to test it. One piece of equipment that can test the chip can cost as much as $1 million, right? To run different sequences of stimuluses on the chip to do all sorts of testing. The facilities that kind of offer this, to set up one anywhere between $1 to $10 billion. So it's quite an expensive business. So now maybe you can understand why nobody dares to attack Taiwan. Nobody dares, because they are the backbone of semiconductor industry, right, to making chips. So big names, Cadence, Synopsys, Mentor Graphics, and Keysight are like key vendors for providing software to design, simulate, layout, all that kind of stuff. So your EDA software. Big names in the production of chips, right? So TSMC gets kind of like Gerber files for a chip, right? Global Foundries. Global Foundries was part of, I believe, AMD. AMD spun off their production and made a separate company. I think like United Emirates one of their holding companies has a lot of stake in Global Foundries. Samsung, that's funny. Samsung, who makes Samsung phones, is making chips actually for Apple. Right? Big names in semiconductor, Qualcomm, right? Every freaking one of these phones has a Qualcomm chip in it for handling Wi-Fi, Bluetooth, cellular communications. And TI, Texas Instruments, analog devices, big mixed signal analog guys. Apple and Samsung, you wouldn't say Apple is a chip producer, but guess what? They are becoming. They said, the only way I can stay competitive in the market, I'm going to design my own chip. I'm going to let TSMC make it. I just don't have the knowledge, the time, the economics of it to make it. So I'll let Samsung make it and TSMC, but I'm going to grab that chip and design it for me to get the best product. So companies are getting into IC design out of necessity to stay competitive in the market. Yeah, so we today use these little black things in the little chips that are bonded inside, but that's kind of what you see is just like a tip of an iceberg. What goes in the background is, whew. All right, so there's an interesting thing that happens kind of in this IC design world, which is, I don't know, commoditization or whatever, democratization of IC design. It says, okay, so let's say about 10, 15 years ago, my wife asked me, said, can you work remotely in what you do? I said, first of all, no, that I can't work in IC design remotely. And not only that, and we wanted to move back to Bosnia, we live in the United States. I said, there is no IC design at that time, 10 or 15 years ago, maybe 20 years ago in Europe, period, right? A few companies like Infineon or something. In the next, and then you have this problem with the very expensive EDA tools, the product process development kits. So that's the ingredients that TSMC gives you. So these are the transistors I have. This is what you can use to make your chip. We're very secretive. They don't want to give it to you, right? Or you have to have special contracts. Then complexity of dealing with the factory. Like, it's just mind-blowing, right? Today, I take my Gerber files, upload to some, Chinese company website, and, board comes back to me. I wish that was easy with, IC. But anyways, so with all these different issues in the industry, Google comes along and says, hey, there's a lot of smart people in the world. They don't have access to the PDKs, process development kits from the, big factories. Tools are very expensive. I don't know how to deal with, with the offshore assembly and test facilities, right? Let's make some open source design moves, right? So they partner with Skywater, which is a US foundry. It's a company that produces chips. And they say, give us your process development kit, so for 180 nanometer, 130 nanometer. So this would be like a dinosaur, kind of compared to where the technology is today. But they opened it. They said, you can download the PDK, no problem, use it. And there is a rise of these open source tools. So people came like, okay, you gave me the PDK. I understand what you have in your foundry. I know the models, I know how your transistors behave, all the parameters, right? The model of the transistor. Now I can start using that and put it in some, free open source tools and start making my own schematics and layouts and chips. And then there's a rise of these, startups for a few $1,000s. They will take your design and they'll push it through some factory. Without, we put our different chips together on one wafer. Everybody gets a piece of the pie, and you can make it. So there's this big move to let the, there's a guy. He says, I want my 14-year-old to design a chip in the garage, right? Kind of that's his mentality. He wants to make that so open. All right, I apologize for running over. I have some books here that if anybody wants to kind of just to open up the old wounds and see what a digital design looks like, analog design looks like, different topics, because this was like a fly over thing, and some books if you guys wanted to look at. So there's a thing floating around. Maybe you can see one of these chips bonded out in a package with a little binocular there. Sorry for taking this long and speaking this fast. Any questions?
We have time for questions.
We do have time for questions. Yeah.
Kemal, thank you for a great presentation and sharing your knowledge here with us. That salary of IC designer is pretty lucrative.
Yes.
It might be a bit late for me, but for students, what would be career path that you would recommend for someone who's interested to do something like this?
Yeah.
Some tips from your end, what to pursue, what kind of education, positions, companies,
Yeah.
and so on.
Yeah, funny thing, I was looking through my old textbooks, and I'll circle this around. I found an interview schedule from Maxim back in 2005. We were interviewing a mid-level IC designer, and there's some topics here that we were going to ask the band gap references. Is the circuits that produce very accurate voltage. Without having you to go with the voltmeter and adjust it, right? It generates accurate voltage based on silicon properties, band gap references. Power supply rejection ratio, buck and boost control mechanism, data converters, right? bipolar transistors, matching, thermal shutdown, MOSFET, sizing, power issues, current sensing. So all these, we would actually, I brought this to that interview. That was, I would bring circuits like this and say, hey, tell me what you see, analyze, obviously you can't calculate anything probably. So I'll circuit this if you guys want to see. So how would you, you have to go back to, you can circle this around, go back to the basics, right? Learning about, or take one of my courses, be my student. IC design courses. So you have to decide where you want to be, right? If you want to do circuit design, right, you don't want to go learn, the chemicals and the materials, when they etch the patterns and, the reticles and the light and all this kind of stuff. That's manufacturing. There's plethora of kind of these textbooks that kind of go through that process. I kind of listed a couple of them here. But yeah, it is a different breed of EEs. I was joking, many of them are kind of borderline brilliant, borderline crazy. That's why he gets paid a lot of money. But and I left that. I left that field, so I wouldn't approach the line. Yeah, it is definitely a challenging field. I mean, just imagine this, right? You're designing a chip. Your mistake and some wiring somewhere could cost a couple of $1 million, right? If the chip comes back and it's not functional, right? So, thank you. I'll be around. You can guys talk to me later.